We're going to be looking at some periodic trends that can be explained by quantum mechanics. The first one we're going to look at is trends in the size of atoms. And so we first have to decide, well, how are we going to define atomic size? Because although we often depict them as solid spheres, atoms are not solid. So how do we measure them? Well, we're going to talk about the radius, and there's different ways to measure atoms. One way is called the non-bonding atomic radius, and this is half the distance between adjacent nuclei in the atomic solid. So you look at the solid of that element, we can measure where the nuclei are, distance between those divided by 2, there's the radius of the atom. We can also look at a bonding atomic radius, also known as a covalent radius. So for nonmetals, this is going to be half the distance between the radii of two atoms that are covalently bonded together. And this is going to be smaller than the non-bonding radius because when atoms bond together, they kind of squish into each other. For metals, it would be half the distance between two of the atoms next to each other in a crystal of the metal, which is going to be really similar to the non-bonding atomic radius. So those are two different ways to measure the size of an atom. We're just going to refer to atomic radius as an average radius based on a whole bunch of different measurements, measuring the atom in different compounds and different elements in different forms. So this is a more general term. And for covalent bonds, we can approximate the length of a covalent bond as the sum of the atomic radii of the two bonded atoms. So now that we know what we're talking about in terms of atomic radius, we can look at the trend. So this is a graph of radius in picometers as a function of atomic number. And so it looks kind of like a big mess. But if we look at these blue elements here, those are the alkali metals. And so we can see a trend in their size. As you go down that column, lithium, sodium, potassium, rubidium, cesium, the size of the atom gets larger. And the noble gases are over here. We can see that as you go down that column, they also get larger. And this makes sense because as you're going down a row, you're going to be increasing the highest principal quantum number, right? So helium has its valence electrons in the first level, neons in the second level, argons in the third level, etc. So we're adding electrons to larger orbitals, and so the atom gets larger. Going across a period doesn't make as much intuitive sense. So going down, we see that the radius increases, which makes sense because these are heavier, they're bigger, right? When we go across a period, across a row, the general trend is that the atoms get smaller. And that's a bit counterintuitive. Because, neon has more protons, more electrons than lithium. Lithium. And yet it's smaller, right? That's not what we would expect. So what's going on here? Well, this has to do with the shielding that the outer electrons experience. So in multi-electron systems, we've got electrons being simultaneously attracted to the nucleus and repelled by each other. So the outer electrons get shielded from the nucleus by the core electrons, which causes those outer electrons to not experience the full charge of the nucleus. And because they're not experiencing the full charge, they are not pulled in as tightly. So here's that diagram of the lithium atom again. So here's the nucleus with a positive 3 charge. The core electrons, there's 2 of them in this first level, and they're like a standing wave, a cloud around the nucleus. And here's our valence electron in the second level. And so as it looks at the nucleus, it has to look through the haze of these other 2 electrons. So these 2 electrons essentially cancel or neutralize 2 of the positive charges on the nucleus. So there's actually 3 positive charges on the nucleus, but because there's 2 negative electrons getting in the way, subtract that, and the effective nuclear charge is approximately 1. So this electron sees a +1 charge. Does that make any sense? So we talk about effective nuclear charge, and that's the actual nuclear charge minus the core electrons. So those are the ones that are getting in the way. Valence electrons make a very small contribution to shielding, and so we're just going to ignore them because we can. So let's look at nitrogen and argon and see what the effective nuclear charges are for those. So for nitrogen, how many protons does nitrogen have? 7, right? It's element number 7. So the actual charge on the nucleus is +7. And there are 7 electrons in total, right? How many valence electrons does nitrogen have? 5. It's got 5 valence electrons, and we know that because it's in group 5A. So this is the total number of electrons, and these are the valence electrons. The difference between those is the number of core electrons. So S, this S here being the core electrons, is 7 minus 5, so it's 2 electrons. So our effective nuclear charge is equal to the actual nuclear charge minus the number of core electrons, and so we have an effective nuclear charge of +5. Let's look at argon. How many protons does argon have? 18. So that tells me it also has 18 electrons, right? How many valence electrons does argon have? 8, right? It's in group 8. So 8 valence electrons. So total of 18 electrons, 8 of them are valence electrons, the rest of them are core electrons. So S, the number of core electrons, will be the total number minus 8, so 10 core electrons. So the effective nuclear charge here is going to be 18 minus 10, which equals +8. You can do these calculations like for neon, and you're going to end up with the same number. So atoms in the same groups have the same effective nuclear charge in the main group. So argon has an effective nuclear charge for those outer electrons of +8. So those electrons are more attracted to the nucleus. They're going to get pulled in, and that atom's going to be smaller than one with a lower effective nuclear charge. So moving down a column, we see that the principal quantum number of the valence electrons is increasing, and so that gives us larger orbitals, larger atomic radii. Moving across a period, the effective nuclear charge is increasing while the principal quantum number is staying the same. So if we're not looking at the charge or the effective charge in the nucleus, adding more electrons to the same principal quantum level, those are about the same distance from the nucleus. But now as we go across, the effective nuclear charge of the nucleus is increasing, and so the electrons get pulled in. So we get a stronger attraction between the valence electrons in the nucleus, and we get smaller atomic radii. Questions? What about the transition metals? We see the same trend in group size as we go down in a column, just like the main group elements. But as we go across that D block, there's a lot less difference in size than we see in the main group elements. The valence shell is actually not that D block, so what we're adding essentially is core electrons, and it doesn't really affect the nuclear charge. And so basically, the transition elements within a period are going to be all roughly the same size. Yeah?
Are the F block elements, are they lumped in with the transition metals, or are they separate from?
That's a good question. Are the F block elements considered transition metals? That's a good question. I never thought about that.
I didn't know, like, where they draw, like, is it only the D blocks are considered?
Well, we're definitely not going to be predicting any trends for the lanthanides and the actinides.
Okay.
Yeah. There's a lot of them are radioactive, and we don't even know what their mass is, because we can't keep enough of them together long enough to measure them or do anything with them.
Okay, so we don't know
Yeah.
enough about them.
So, I mean, those guys are cut out of the periodic table and just kind of stuck at the bottom, because most of them, not really important. Uranium is important. That's really the only one. The rest of them are pretty obscure, unusual. It's a great question, though. So let's go back to this graph for a minute. So looking here from lithium to neon, that's where we're going across the period, and we see that it's getting smaller. From sodium to argon, getting smaller. Here in the green, those are the transition elements in period 4. And so we see, I mean, there's a little bit of variation here, but it's not really a good trend. So those guys are just very close in size. So what do we need to be able to do with this? We should be able to pick the larger atom in a pair just by looking at the periodic table. So let's practice that. On the basis of periodic trends, choose the larger atom in each pair if possible. So we need to find these guys. So our first one here is tin and iodine. Here's tin, and here's iodine. So then we need to be able to remember these trends. So as we go down, they get bigger. And as we go across, what happens? They get smaller because of that effective nuclear charge. So here, these two elements that we're comparing, they are in the same row, the same period. So which one is larger? Tin will be larger because as we go from tin to iodine, the trend says they get smaller. So out of tin or iodine, we would say that tin is probably larger. Germanium or polonium. I'm going to find these guys. Here's germanium, and here's polonium down there. So these guys are at a diagonal, right? So if we're going left to right, polonium is to the right, and the trend would say that polonium is smaller. But if we're looking vertically, going down, it gets bigger, and that trend says that polonium is going to be larger. So a fair answer here would be not possible, because the two trends are opposing each other. So we could say it's not possible, especially since it gave us that out up here. Now, if you had to choose, this vertical trend is more important than the horizontal trend. And so if I had to choose one, I would choose polonium. But I won't do that to you on an exam. And then let's look at chromium and tungsten. So there's chromium and tungsten. Which is bigger? Tungsten. The one that's lower is bigger. Any questions? We're going to learn several different periodic trends. And they either have the same trend as the size or the exact opposite. And so we'll try to reason out what's happening.